Okay, last video in chapter 4, so we're going to finish it up today. Okay, we talked about stoichiometry last time. We talked about going from grams to moles to grams, but you don't always have a solid reacting with a solid or a liquid reacting with a liquid. Sometimes in the laboratories we have solutions and we do reactions in aqueous solutions. So that's where solution stoichiometry comes into play. So, we've talked about grams and moles. Well, now we're going to throw an extra thing in there, and that would be volume. So it's kind of a second gear here. So let's talk a little bit about solution stoichiometry in this particular video. In solution stoichiometry, use molarity as a factor. So we've kind of mentioned, I think, briefly before. So, for example, given the following equation, I can take copper sulfate, and I can, a solution of copper sulfate here, I can react that with sodium hydroxide. And what I get is I get copper 2 hydroxide, I guess that's copper 2 sulfate, copper 2 hydroxide plus sodium sulfate. Okay, I forgot to put the AQs in here, but they're all aqueous. All right. So given that balanced equation, of course there's a 2 in front of the sodium hydroxide there, what volume of 0.2 molar copper sulfate solution is required to react with 50 milliliters of 0.1 molar sodium hydroxide? Okay, so first thing we ask ourselves is, what do we know here? All right, we know three things here. Well, we know we have a solution, and it's 0.2 molar copper sulfate. We know we've got a 0.1 molar sodium hydroxide solution, and we know we have 50 milliliters of that. All right, so which one of those three am I going to start with? Well, when you see molarity in a problem or a concentration unit, generally what you're going to do is you're going to use that as a factor. So don't start with the molarity. Always start with the other piece of information first. So the other piece of information that we have here would be the 50 milliliters. So that's where we're going to start. Molarity means what? Moles per milliliter? No, it means moles per liter, correct? So what do you think of the first thing I need to do to this 50 milliliters is? Well, I need to change that to liters, because molarity is moles per liter. So to change to liters, I'm going to divide by 1,000, or you can move your decimal 1, 2, 3 places back, and you end up with something like this, 0.0500 liters of your sodium hydroxide. And that's where we're going to start. So we draw a factor. Okay? All right, where are we trying to get to? Well, what volume of 0.2 molar copper sulfate? So we're trying to get to liters of copper sulfate solution. So we're in liters of sodium hydroxide, and I need to liters of copper sulfate. Can I say for every 1 liter of copper sulfate solution, that's going to react with 2 liters of sodium hydroxide? I can't say that, because coefficients in a balanced equation are not liter to liter ratios either. They're mole to mole ratios. Right. By the way, if they were the same concentration, actually I could do that, but that's simply because 1 mole of this would, react with 1 mole of that. But no, you can't go from liters to liters. All right, that's moles to moles. So if I've got 50 milliliters, which is 0.050 liters of sodium hydroxide, let's see if I can get to moles of sodium hydroxide somehow. Okay, if I can get to moles of sodium hydroxide, then maybe I can get to moles of copper sulfate, and if I can get to moles of copper sulfate, maybe I can get to liters of copper sulfate somehow, some way. Does that make sense? All right, well, do I know a relationship between moles of sodium hydroxide and liters of sodium hydroxide solution? Well, I do, because that's what 0.1 molar means. 0.1 molar means for every 1 liter of sodium hydroxide solution, there are 0.100 moles of sodium hydroxide. So what goes on top, what goes on bottom? Well, you want the liters on the bottom, sodium hydroxide, cancel out with the liters of sodium hydroxide here again. Again, always put your label it. Just don't put liters, don't just put 0.05 liters of sodium hydroxide, 1 liter of sodium hydroxide. If you don't put your labels in there, you're not going to know what to cancel. And that's the whole reason you're stringing this thing out, is so that you'll know what to cancel. So don't get lazy on me here. All right, so 1 liter of sodium hydroxide solution, 0.1 moles of sodium hydroxide. That's what 0.1 molar means. Okay? All right. Well, that's moles of sodium hydroxide. I'm trying to get to liters of copper sulfate. Can't get there directly. Where might I want to go next? Well, can I get to copper sulfate somehow? Anything with copper sulfate in it. Well, here's copper sulfate in my balanced equation. Here's sodium hydroxide. Do you see for every 2 moles of sodium hydroxide I react, 1 mole of copper sulfate reacts with it? Because that's coefficients of your balanced equation. See, anytime you need to go from moles of something to moles of something else, you always use your coefficients in your balanced equation. Okay, well, what goes on top of what goes on bottom? Well, 2 moles of sodium hydroxide down here on the bottom, 1 mole of copper sulfate up here on the top. Why do I do it that way? So my moles of sodium hydroxide cancel, and I'm left with moles of copper sulfate. But what we were asked for was volume of copper sulfate. In other words, liters of copper sulfate solution. So how do I get from moles of copper sulfate to liters of copper sulfate? Well, there's my molarity, see? The molarity tells me that. Okay, 0.2 molar, what does that mean? Well, it means for every 1 liter of copper sulfate solution, there are 0.2 moles of copper sulfate dissolved in it. That's what 0.2 molar means. So 1 liter of copper sulfate solution, 0.2 moles of copper sulfate. 0.2 moles of copper sulfate, 1 liter of copper sulfate solution. What goes on top, what goes on bottom? Well, you want to put the moles of copper sulfate on the bottom so that you can cancel your moles of copper sulfate up here on the top. What am I left with? Liters of copper sulfate solution, which is volume, which is what we were looking for. So we do the math. So 0.0500 times 0.1 divided by 2, and then divide that again by 0.200. Let's see, 3 significant figures here, 3 here, 3 here. The rest of these are exact, so therefore 3 in my final answer, and that would be 0.0125 liters of copper sulfate solution. Okay? Now, if we're mixing things up in the laboratory, chemicals in the laboratory, then yeah, we might deal with liters of something. All right? But when you're in the laboratory, do you normally deal with liters of stuff? Well, no, normally you deal with milliliters of stuff. So how would I convert that to milliliters? Well, we just take our decimal here, and we move it back 3 places to the right, 1, 2, 3, or multiply by 1,000, however you want to look at it. And what we get is we get 12.5 milliliters of copper sulfate solution. All right? And so if you gave me this up here, that's fine, because I asked you what volume, and you gave it to me in a volume unit, so I guess I really can't count that wrong, can I? But if the problem said, how many milliliters of 0.2 molar copper sulfate solution? Well, then you'd probably have to convert that to the 12.5. Or if it said what volume is required, and your choice is A, 10 milliliters, B, 12.5 milliliters, C, 50 milliliters, D, 100 milliliters. You know, if the answer's already in milliliters, and then I guess you need to be able to convert back to milliliters to see which one of those is the correct answer on the test. But yeah, if I just asked you the volume, you gave it to me in liters, I guess I can't count off for that because you did give me the volume. All right, but mainly we deal with milliliters in the laboratory, so it's useful to be able to convert back there. And that's kind of how it works. Look, basically what it all comes down to is this. This is, I think, worth remembering. If I need to go from moles of something to atoms or molecules of something, use Avogadro's number, 6.022 times 10 to the 23rd. If I need to go from moles of something to grams of something, or grams of something back to moles of something, use your formula mass. If I need to go from moles of something to moles of something else, use your coefficients in a balanced equation. And then if I need to go from liters of solution to moles of solute in that solution, or moles of solute in that solution back to liters of solution, use your molarity as a factor. All right, so see, solution stoichiometry is just one more thing on top of what you already know how to do. If you think of it that way, it's not that bad. Yeah, you can string a lot of factors out here when you're doing it, but again, it's just one more thing on top of what you can already do. So if you think of it that way, maybe it's not quite as bad, I guess. Okay, this next problem here it's not very difficult mathematically, but conceptually you have to get this in your head. You have to understand what's going on to be able to really go any further, especially if you're dealing with solution stoichiometry or anything like that. And guess what? Chem 2, it's all solution stoichiometry. It's all molarity. So yeah, this is something that's going to become important to you somewhere down the road. All right. So determining moles of ions in a solution. Okay, so what are the molarities of aluminum 3 plus and sulfate in 0.1 molar aluminum sulfate? Okay, so how can a solution have 3 different concentrations? Well, remember, your concentration depends on the number of moles of what you're looking for over the liters of solution. But it also depends on exactly what you're measuring. You know, I could have a Dr. Pepper solution that is highly concentrated in sugar, but very dilute in salt. You know, it depends on what I'm looking for there. All right, so what are the molarities of this 0.1 molar aluminum sulfate solution in aluminum 3 plus and also in sulfate? Okay, to do this problem conceptually, you have to be able to visualize this particular fact, and this is important. When I take a soluble ionic salt and I put it in water, how does it go into solution? Does it go into solution as one big molecule? No, it breaks apart into its ions. You know, your polyatomic ion stays together. You know, like a sulfate, for example. A sulfate's not going to break up into a sulfur and 4 oxygens. That stays together as a unit. But my aluminums and my sulfates don't go into solution as one big giant molecule. The water, if it's soluble, separates into the ions. Okay? So here is kind of a graphical representation of aluminum sulfate. So here's my 2 aluminums, which are +3 charge. Here's my 3 sulfates here. So this is basically this. What keeps everything together is the fact that I've got opposite charges. And so opposite charges attract. Again, not the exact crystal structure, but you know, it'll do for now. Okay? When I put that in water, bust everything up. There's something about that water molecule that's able to get in between these ions and separate them from each other and keep them separated from each other. All right? That's what makes that salt soluble. All right? So if I put this in a water solution, what does it look like now? Well, I've got aluminum 3 plus here and aluminum 3 plus here. And I've got 1, 2, 3 sulfates floating around from this. Does that make sense? Okay, if you can visualize that, think of it this way. If my concentration is 0.1 molar in aluminum sulfate, what is my concentration in aluminum 3 plus? Well, every time I put 1 aluminum sulfate in the water, how many aluminum 3 pluses do I get? Well, I get 2. See? So do you see that there's twice as many aluminum 3 pluses floating around in that solution as aluminum sulfates that I started with? Okay. Well, if my original concentration of my aluminum sulfate was 0.1 molar, do you see that the aluminum 3 plus concentration is going to be 2 times 0.1 molar? Because I've got twice as many moles floating around in there in the same volume, so therefore the concentration is twice as much. Twice as many little particles here. Okay? I can do that. I mean, I'm not violating the law of conservation of mass, because we're not talking about mass, we're talking about moles. There is no conservation of moles. This mole is a lot bigger than these 2 moles over here and these 3 over here. So yeah, whatever this weighs over here is equal to what this weighs over here, but there's no conservation of moles. I don't have to have the same number of moles on both sides. All right? So if I have twice as many moles in the same number of liters, the concentration of aluminum 3 plus is 0.2 molar, not 0.1 molar. And these brackets around the species, that's a shorthand way of saying what is the concentration in moles per liter. That's what that means. Okay? So the math is not very difficult here, but conceptually you have to get this in your head. All right? What is the concentration of the sulfate here? Well, for every 1 aluminum sulfate, I get how many sulfates? I'll get 1, 2, 3. So I have 3 times as many moles as what I originally had here. So my concentration is going to be 3 times the 0.1 molar. It'll be 0.3 molar. And again, this means concentration in moles per liter. All right, so the math is not very difficult there. But conceptually, you have to be able to visualize that, because that's going to become important here in a minute. And it's also going to be very important in Chem 2. So stop and think about that if you have to before we move on. All right, well, if you can do that, now I guess you can do this one. So how many moles of chloride ions are in 1.35 liters of 0.255 molar aluminum chloride? Okay, so to do this problem, the first thing you have to be able to do is you have to be able to write the formula for aluminum chloride. All right, so aluminum forms what type of ion in a water solution? Well, it's +3. Okay, chlorine is found in group 17 of the periodic table. Those are your halogens. What type of ions do they form? Those form -1. So what's the smallest number of little +3s and -1s I can put together and get something to add up to 0? Because remember, in ionic compounds, it has to all add to 0. It doesn't. If you can't count to 0, you have done it wrong. Start again. Well, 3 of these little guys here, these little chlorides, and 1 aluminum 3+. 3 of these gives me a total of -3, +3, this is neutral. So there's aluminum chloride. So that's the first thing you got to be able to do. All right. Second thing you got to be able to do is you got to realize, hey, when I put aluminum chloride in water, and it is soluble, how does it go into solution? What doesn't go into solution is a big giant aluminum chloride, because it's an electrolyte. It breaks apart into ions. So I'm going to get an aluminum 3+, and I'm going to get 3 chlorides. See, these chlorines, I'm not going to get a Cl3, 3-. These chlorines aren't going to stay together. These sulfates don't stay together up here. They're negatively charged. Why would they stay together? You know, like charges repel, right? So again, bust everything up when you put an ionic compound in water. Well, what do we know here? Well, we know we've got a solution, and it's 0.255 molar in aluminum chloride. What else do we know? Well, we know we've got 1.35 liters of it. What am I going to start with? We're going to start with the 1.35 liters. Always start with the other piece of information first. Don't start with the molarity. So that's why we wrote down this here. Okay, time sign, factor. Okay. Where am I trying to go to? I'm trying to go to moles of chloride. Do I know a direct relationship between liters of aluminum chloride solution and moles of CO-? No, not even close. What do I know a relationship between? What would help me get there? Well, maybe if I could get to moles of aluminum chloride here, here's a relationship between this and moles of chloride. So maybe if I can get to moles of aluminum chloride, that would help me. Well, do I know a relationship between liters of aluminum chloride solution and moles of aluminum chloride? When I need to go from liters to moles to liters, what do I use? Use your molarity right here. I know there are 0.255 moles of aluminum chloride for every 1 liter of aluminum chloride solution. So what goes where? I want the liters on the bottom, and I want the moles on the top, so I can cancel out the liters. And that leaves me with moles of aluminum chloride. Make sense? Okay, but we're looking for moles of chloride. So time sign, another factor. Do I know a relationship between aluminum chloride, moles of aluminum chloride, and moles of chloride? Yes, I do. How do I find that? Well, moles of something to moles of something else. Look at your coefficients in your balanced equation. Okay. See, the only difference between this and that one way up there is you wrote the equation. It wasn't given to you. But it's still a balanced equation. And that's how you get from moles to moles. So for every 1 mole of aluminum chloride, I can make what? 3 moles of chloride in there. All right, so 1 mole of aluminum chloride, 3 moles of chloride ions, moles of aluminum chloride on the bottom, so they cancel with these moles of aluminum chlorides, and we're left with moles of chloride, which is what we're looking for. All right, so I got 1.35 times 0.255 times 3. Looks like 3 here, significant figure-wise. The rest of this is exact. So my answer needs to have 1.03 moles of chloride ions. And there's your answer. What if, hypothetically, I'd asked you how many chloride ions are there? How would I get from moles of chloride ions to actual chloride ions? Well, that's where you'd use Avogadro's number. You know that 1 mole of chloride ions is equal to 6.022 times 10 to the 23rd chloride ions. And you'd make another factor, cancel out your moles, and end up with the ions. See, it all comes down to that. It's the same thing as this up here. Okay, the only difference here is you have to write your own little equation. And to do that, you've got to realize what happens when you put an ionic salt in a water solution. Bust everything to pieces. Break up all the ions. Don't keep them together. Your polyatomic ions, your phosphate stays together, and your sulfate stays together, and your carbonate stays together. But your carbonates don't stay together. I mean, they would break apart from each other. But other than that, yeah, just bust it all up. Okay? Do you see how you have to understand what's going on here to be able to do this right here? So let's talk about redox titrations. Okay, there's a discussion there about regular titrations, acid-base titrations, and there's one here with redox titrations, but both of them are really just solution stoichiometry problems. They work pretty much the same way. All right, so this is probably, I would think, the most complicated problem, I guess, that you would run into, besides that limiting reactant problem here in the chapter. So, of course, we saved the best for last, right? So this is a redox titration. I can take a solution with dichromate in it. That's what the Cr2O7 2- is. And I can react that with a solution with iodide in it. Iodide, that's that I-, 6 of those. This works better at acidic solutions, so we're going to kick in 14H pluses to get this to go. And that goes to 3I2 plus 2 chromium 3 pluses plus 7 waters. This is a balanced redox equation. And you can balance this using a half-step equation method, which, again, we're going to talk about in Chapter 17. So, not going to make you do it right now. I'm just going to give you the balanced equation. But that's what it is. And someday you'll be able to balance it on your own. Okay, so given this equation, suppose 22.0 milliliters of 0.15 molar potassium dichromate is required to react with a sample weighing 5 grams. What is the percent I- in the sample? Okay, little trick here. All right, the first thing you have to understand is, okay, what am I actually looking for here? Okay, well, I'm looking for the percent I-. How am I ever going to find that? Well, I know how much the entire sample weighs. Does it make sense to you that if I can figure out how many grams of I- are in that sample, I can put that over the total sample weight times 100, and that gives me the percent I-. So really what this problem is asking you for is it's asking you for grams of I-. Does everybody see that? Okay. What am I given here? Well, I know I've got 22 milliliters of this potassium dichromate solution, and I know it's 0.15 molar. So which of these do you think you're going to start with? We're going to start with the 22.0 milliliters. Never start with your molarity, start with the other piece of information. Okay? Molarity, again, is what? Moles per liter, not milliliters. So what do I need to do with this 22 milliliters? I need to change that to liters. So we're going to move our decimal 1, 2, 3 places. And that's where we are here. This is this 0.0220 liters of potassium dichromate solution. All right? Okay, so we've got potassium dichromate here. What are we looking for? We're looking for grams of I-, right? Can I go from liters of potassium dichromate solution to grams of I-? No, definitely not directly. Okay, well, do I know a relationship between liters of potassium dichromate solution and anything here? Well, I know the molarity, and I know that this means there's 0.15 moles of potassium dichromate for every 1 liter of solution. Maybe I could use that somehow. Okay, well, 0.15 moles of potassium dichromate for every 1 liter of potassium dichromate. Again, put your labels in, don't get lazy on me. do it this way because our liters of potassium dichromate will cancel out. What am I left with? Moles of potassium dichromate. So I guess we're getting somewhere, right? So times sign, another factor. Okay. Well, I'll look at the equation. Do you see potassium dichromate up here? No, I don't see potassium dichromate in the equation at all. Do you see I minus? Hey, I see I minus. So, I mean, that's something, I guess. Do you see anything in this equation related to potassium dichromate? Well, here's a dichromate. Do you see if I can somehow get moles of dichromate, I can get moles of I minus. And if I can get moles of I minus, I can get back to grams of I minus, and then I could actually figure out my percent I minus. But I got to get to this moles of dichromate somehow first. So how do I get from moles of potassium dichromate to moles of dichromate? Well, again, what it comes down to is you've got to realize that when you put potassium dichromate in water, how does it go into solution? Well, it breaks apart into its ions. Okay, so what ions do I get from this? Well, I get 2 potassiums, and I get 1 dichromate. See, if you don't know your polyatomic ions, you'd be trying to split this into chromiums and oxygens and all sorts of stuff. Got to know your polyatomic ions. You've got to know that's a dichromate when you see it. It goes together. It's got a charge of -2. Got to know it. That's why I stress that so hard. Okay? All right. So here is the equation for the dissociation of potassium dichromate. Again, very, very much like this problem that we talked about over here that we said conceptually you needed to know. Okay? All right. From this equation, do I know a relationship between potassium dichromate and dichromate? Well, I know for every 1 mole of potassium dichromate, I get what? 1 dichromate. Now I get 2 potassiums, but I don't care. I'm not going to potassium. Potassium's not reacting here. Doesn't matter. What's important is the potassium dichromate here and the dichromate here. So for every 1 mole of potassium dichromate, I get 1 mole of dichromate, and that's where that comes from. Okay, potassium dichromate on the bottom, so that'll cancel, and that gives me moles of dichromate. All right. From here, it's kind of smooth sailing. So I'm looking for grams of I minus. Can I get there from moles of potassium dichromate? Well, no. But can I get to anything with I minus in it? Yeah, I can, because I know for every 1 mole of dichromate, that reacts with what? 6 moles of I minus, right? Because that's my coefficients in my balanced equation here. So what goes on top, what goes on bottom? Well, moles of dichromate on bottom, so they cancel, and we're left with 6 moles of I minus up here on top. Okay, but we're looking for what? Grams of I minus? How do I get from moles of I minus to grams of I minus? Use your formula math. See, it's all the same. It's a little longer problem, but it's the same stuff over and over again. All right. So you look up iodine in the periodic table, that extra electrons, that really don't weigh anything. You get 126.9 grams. Okay, so 1 mole of I minus weighs 126.9 grams of I minus. Moles on the bottom, so they cancel. Notice that everything's canceled except for grams of I minus, and hey, that's exactly what I want. So no more factors. Okay, so 0.0220 times 0.150 times 6 times 126.9. Looks like 3, 3, 4 significant figures. So go with the least, that'd be 3. 2.51 grams of I minus. All right, do you see how that worked? But that wasn't the question. The question is, what is the percent I minus? And ask her how many grams of I minus. So now to get the percent, it's pretty simple. I've got 2.51 grams of I minus. The entire sample weighs 5 grams. Multiply by 100 to get to a percent, 50.2% I minus. And that's how it works. Question. What is the other 49.8% of my sample? Don't know. Could be anything. See? Because this test only tests for I minus. But I know that 50.2% of my sample is I minus. And so if I want to know what else is my sample, maybe I could do another test. Figure out the percent nitrogen, or figure out the percent potassium, or sodium, or whatever, oxygen, whatever happens to be in there. See? And this is how, if you'll remember when we were doing the simplest formula labs, where I gave you percent composition and then you figured out the simplest formula from that. Well, this is one way that you can get the percent composition. See, for if it happens to be a pure substance there, is you could do things like this: test for I minus, test for this, test for that, add it all up, figure out what it is, and then from there you can do the simplest formula. Of course, you've got the molar mass, you can get the molecular formula, and so on and so on and so forth. All right, but at least this tells you exactly how much I minus is in there. Nobody knows what the rest of the stuff is, and of course, no one's going to ask you. Given this equation right here. But that's pretty much how it works. Okay, I guess that's pretty much chapter 4. So we'll see you in chapter 5, and I guess bye for now.